Hi, I'm Reverend Greg, and I welcome you to this video in the tutorial series Shaders for Hobby Programmers. This time we'll look into vignetting and another coordinate system, the texture coordinates. As always, a short disclaimer. This tutorial series is mainly for hobby programmers who struggle with understanding shaders. I'm not a professional programmer and I'm not very good at maths. So if you see any mistakes in my video or see a better way to solve a problem, please add a comment so everyone can learn from you. So let's first talk about the effect we're creating. The French word vignette originates from the word vigne, which means vine, and describes a frame in the shape of vines like in example seen in labels on bottles of wine. In painting and photography, vignette is still used to describe ornaments framing the image. But in photography it's also used to describe the reduction or increase of brightness towards the corners of the image, be it from the lenses or on purpose. Now try to imagine you create this effect with the shader functions and operations we already learned. If we want to vignette the whole screen, we could use GLFrag chord. And honestly, if you are using a vignette in a game, it's probably going to be a post-processing shader effect, and then using GLFrag chord would make sense. But what if you want to use vignette on only a single sprite or surface like a screenshot or a map? Then doing this with GLFrag chord would be possible, but unnecessarily difficult. So in this video we'll learn about vignetting using texture coordinates. The next video will be about vignetting using a coordinate system based on corner ID. But if you want to use a vignette in view space instead, it'll be easy to adapt the code using GLFrag chord instead. Besides, there's several tutorials out there showing vignette with GLFrag chord, so I don't plan to cover that in an additional video. But first let's talk about texture coordinates and what they are. GameMaker Studio stores every sprite on a texture page like this. Every texture page has its own coordinate system, where the upper left corner always is 0, 0 and the lower right corner always is 1, 1. The axes of this coordinate systems are often called U and V instead of X and Y, and therefore a texture page sometimes is called a UV map. The sprite I framed on this texture page has its UV coordinates at 0.43, 0.48 and 0.56, 0.61. And the size of this square sprite in UV coordinates is also square. It's 0.13 wide and high. When we send a sprite to the graphics card, GameMaker Studio creates a plane with 4 vertices, and with each vertex, GMS also sends the UV coordinates of each vertex on the texture page of the sprite. So in our example, the first vertex would have the UV 0.43, 0.48. The second vertex would be 0.56, 0.48. The third would be 0.56, 0.61. And the fourth would be 0.43, 0.61. So the first tricky thing is this. If we want to refer to the top left texel of the sprite, we can't just refer to 0, 0 as we would do with GLFrag chord or with in position. But instead we need to refer to 0.43, 0.48. And of course the lower right corner wouldn't be 1, 1. What makes handling texture coordinates even more complicated is that texture pages don't need to be square. This texture page in example is half as high as wide, but its coordinates still go from 0, 0 to 1, 1, which means although the sprite is square, it has non-square dimensions on the texture page. It's still 0.13 wide, but it's 0.26 high. Or this texture page is half as wide as high. So the square sprite's UVs are not square either. In UVs it's 0.13 high, but 0.26 wide. And as far as I can tell, you cannot force GMS to use square texture pages. You can set the maximum size, but you cannot set if it's square or not, which can become tricky for us. This can be especially tricky when we start using additional textures later in this series. Because if those textures are on different texture pages, those pages could both be square or landscape or portrait, And so two square sprites on non-square texture pages can have different ratios in UV coordinates. What we can easily do, however, is giving a sprite its own texture page. This means the sprite's UV coordinates always range from 0, 0 to 1, 1. But this also means the engine needs to swap more texture pages, which can become a problem especially on mobile devices. Surfaces, by the way, have their own UV coordinates as well, but as sprites on separate texture pages, a surface's UVs always range from 0, 0 to 1, 1 as well. So you can see there's quite some potential in being able to use texture coordinates in a shader, but it can also become a lot more complicated than using glFrag code or in position. There's different solutions to this problem and we look into them in later videos. The ones I can think of right now would be using the corner IDs GMS provides, which we will have a look at in the next video, and creating your own vertex buffers, which we will look into in a later video. Now let's talk about how we can calculate the vignette. Let's assume the vignette is oval-shaped and has the width and height ratio of the image. It can be larger or smaller, but always has the same ratio. So it would look like this. Now let's assume these are the UVs of the sprite on its texture page. The top left UV at 0.2, 0.25, and bottom right UV at 0.6, 0.45. The first thing we need to get is the center. That would be easy if we know the image's UVs go from 0, 0 to 1, 1, like on a surface or with a sprite on its own texture page. Then the center would always be 0.5, 0.5. But with UVs on a mixed texture page, we need to calculate the center. Luckily, that's not hard to do. To get the center, we can add half the width and height of the sprite on the texture page to the top left UVs. So in our example, the center would be 0.4, 0.35. Now we need to get the distance from each pixel or fragment to the center. As in the last video, we'll subtract two point vectors from each other and then use the GLSL function length on the difference to get the distance of those 2 points. The first vector is the center of the image on the texture page as just calculated. The second vector is the coordinate of the current fragment on the texture page. Having a quick look at the vertex shader, we can see a vertex attribute vec2 in texture chord. That's the vertice's position on the texture page in UVs. We also see a varying vec2 VV text chord, which will be passed on to the fragment shader. And inside the main function of the vertex shader, VV text chord is set to the vertex attribute in texture chord. Whenever we calculate a varying from a vertex attribute in the vertex shader, the varying will be passed to the fragment shader as an interpolated value for each fragment between the vertices. And because of that, in the fragment shader, the varying VV text chord is interpolated to the fragment's coordinate on the texture page. So the second vector we need to calculate the vignette, the fragment's position, is VV text chord. We will use the length of this new vector to determine how much this fragment gets vignetted. But now we run into a problem specific to UVs. Our distance is based on the UVs, but the same sprite on another texture page might have much larger or smaller dimensions. And also there's the problem that we want the distance from the top to the center to be the same as the distance from the sides to the center if we want that oval shape. But our image is clearly not square, so we need to fix that somehow. Unfortunately, there's a simple solution again. We can normalize the distance vector by dividing its UV components by the UV dimensions of the sprite and then calculating the length. Now the distance from the sprite's center to the border of the sprite is always 0.5. The next step is to add a fall-off range towards the center of the image. We can easily do that with the by now hopefully familiar smooth step function. We smooth step from the outer range to the outer range minus the fall-off range by the distance of the fragment to the center. And in the end, we just multiply the result of smooth step with the color of the fragment to apply the vignette. But now let's finally switch to GameMaker. I'm going to use this sprite from the base project to test the vignette on, but you can use any sprite you want. For now, let's set it to use a separate texture page. In GMS1, the setting is called Use for 3D or something similar. This makes sure the UVs of the sprite range from 00 to 11. We will uncheck this setting later. Let's start with creating the object. I'll just duplicate the template module and name it Object Vignette by Text Code, and move it to a new folder I called Masking. In Create Event, the only regions we need are Title Info Corner Click and Sprite and Shader, so let's just delete the rest. Now in the title region, I'll add the title text and info text for the base project. Inside the sprite and shader region, I'll set the sprite to the one I just showed. And as shader, set shader vignette by text code. We'll create this shader in a few seconds. Now we won't need the step event and can just remove it. And in draw event, I'll just make sure the sprite gets drawn by the shader. Now we can create a new child of the template room and call it room, vignette, vertical line, VV text code, and corner ID. XXV will add a vertical line and XXA will add an AND. We will reuse this room in the next video about corner ID, by the way. I'll place the object on the main layer's top center. We'll use the lower row in the next video as well. And on the modifier layer, I'll stretch the kill modifier so we only get 3 sliders and no buttons. Let's continue with the shader. I'll create a new shader and call it Shader Vignette by Text Code. The vertex shader can stay as it is for now. We'll come to it in the end for a tiny optimization. In the fragment shader, all we do for now is split the glfrag color line and test what VV text code actually means by setting the color to VV text code X. Let's run the program in debug mode now so we can see the result. We had set all the color channels to text code X, and we see the color range from black to white from left to right, which means VV text code X is going from 0 to 1. And since the sprite is on its own texture page, this means the sprite's UVs go from 0 to 1. If we click the pause button on the debugger, switch to the graphics tab and refresh the textures, we can see the sprite on a separate texture page. Note that the texture page is a bit larger than the sprite in my case, since the dimensions of a texture page are always a power of 2. But UV11 still is the bottom right corner of the photo and not of the texture page. I'm not sure if that's how GPUs work or if GameMaker is helping us out here. So let's go back to the sprite's options, uncheck separate texture page, and run this again in debug mode. Now you can see the colors won't go from black to white anymore, which means VV text code is not going from 0 to 1. And if we pause and check the texture pages again, we can see why. Its UVs are not 0 to 1 anymore because the sprite is sharing the texture page with other sprites. Let's continue with the fragment shader and get that vignette in. We will need several uniforms for this shader. I'll create 3 uniform floats to control the vignetting. Vignette opacity will determine how much the colors are darkened. Vignette outer will be the outer oval size in % of the image. So 0.5 will be what we saw in the intro of this video. The oval will touch the frame of the image. And vignette falloff will be the falloff from the outer ring towards the center. Of course, you could flip the way the shader calculates by setting an inner range and a falloff away from the center. For me, it was just easier that way. We'll also need two uniform vec2. UV center will be the center of the sprite on its texture page, and UV dimensions will be the width and height of the sprite on the texture page. Now in the main function we do the maths we've seen in the beginning of this video. First let's get the length of the vector from the fragment to the center in UV space. So float len is length of VV text code minus UV center divided by UV dimensions. Then the vignette factor. Float vignette is smooth step, vignette outer minus vignette falloff, and length. Now we need to factor in the opacity uniform with a mix function. So base color RGB is a mix of base color RGB and base color RGB times vignette by the mix amount of vignette opacity. And in the end we just change the glfrag color line to base color. Now back to the object's create event of our test module. Here we need to get the uniform handlers for all 5 uniforms we just created. uVignette opacity, uVignette outer, uVignette falloff, uUV center, uUV dimensions. And for those UV uniforms we need to actually get the UVs from the sprite and then calculate the center and the dimensions. To get the UVs we can use the function spriteGetUVs. This function returns an array with UV data on the sprite. Entry 0 will be the left X, entry 1 the top Y, entry 2 the right X, and entry 3 the bottom Y. The array actually has 8 entries, but we won't need the rest for this shader. So we'll get the UVs and store them in a local variable. Now we can store those 2 UV pairs we need for the uniforms. First the dimensions. UV width is UVs 2 minus UVs 0. UV height is UVs 3 minus UVs 1. UV dimension 0 is UV width. And UV's dimension 1 is UV height. And then the center. UV center 0 is 0.5 times UV width plus UV 0. And UV center 1 is 0.5 times UV height plus UV's 1. And finally I want to set the caption of our 3 sliders. One for the vignettes alpha, one for the outer range, and one for the falloff or inner range. In draw event I'll first set up the local vars for the uniforms. Vignette opacity is slider value 0, vignette outer is slider value 1, and vignette falloff is vignette outer times slider value 2. So opacity will go from 0 to 1, as will the outer range. Just as a reminder, an outer range of 0.5 means the vignette will touch the sprite's edges. And the falloff I'll just multiply with the outer value. So it's going to be a percentage of that. If you're not using the base project and want some hard-coded values, opacity 0.5 or above will be too much in the game, but good for testing. Outer at 0.5 to 0.8 will be great, and falloff just needs to be lower than the outer value. Now we can pass those uniforms. The UVs we can pass as arrays to the vec2 uniforms of our fragment shader. And the vignette parameters we can pass as floats. So now let's run this and test if it works. And it seems to work nicely. We can change the opacity, the outer ring, and the falloff. Now all I'd like to do is a tiny optimization. In the fragment shader we calculate the length of the vector from a fragment to the center of the image. The vector being VV text chord minus UV center divided by UV dimensions. This vector can be calculated in the vertex shader and then it only needs to run once per vertex. And since VV text chord is interpolated when being passed to the fragment shader, this will keep working for each fragment. So let's copy the vector calculation inside the length function. In the vertex shader, I'll declare a new varying vec2 and call it VV_FragUV. And since we're doing the UV calculations in the vertex shader, we need to declare the two vec2 uniforms, UV center and UV dimensions. Now we can calculate the new varying with the line we copied from the fragment shader. And close the vertex shader. In the fragment shader we need to add the varying as well. But we can remove the two vec2 uniforms since we moved the UV calculations to the vertex shader. And inside the length function, all we need to do is replace the calculation with the new varying VV_FragUV. If we run this program again, we shouldn't see a difference to before. And we don't, so that worked. So this was my basic overview on texture coordinates. I hope you learned a lot and enjoyed this video. In the coming video, we'll have a look at corner ID. Until next time.